Hello again everyone, welcome back to ptet.chemistry channel. So this is Mr. On. In this video, I'll talk about very fundamental concepts on relative isotopic versus relative atomic masses. So I'll exemplify with some calculations mostly in this video. But before I do, actually, you should really know the definitions as required by the all the UK examination body and in fact all across the world. When people deal with relative masses, okay, you need to think about what is atomic, what is molecular, and what is formular mass. So they all refer to similar kind of thing, but it's different from isotopic, relative isotopic mass. Okay, so relative isotopic mass is just the ratio of mass, whereas all of this is the ratio of mass. Is the ratio of average mass. Okay, so that's important to differentiate. These are all average masses, whereas this is an exact mass. It's the ratio of mass. Okay, and they all have similar kind of idea, and you have to get all the technical terms correct. And unlike definitions which you just memorize by heart, there's also something called memorizing by understanding. So you got to know the how to tell the story, how to make sense of it. All right, it's a ratio. It has no unit. When you compare, it's the ratio of mass, so it's the mass of one thing relative to another thing. So the unit gram is to gram, kilogram is to kilogram. Eventually they'll give you no unit, so that's why it's a ratio of mass. All right, but here is the ratio of mass of one atom of an isotope. Okay, so it's a particular isotope. So ratio of mass of one atom of an isotope relative to or compared to, really it's up to you which word you use, but they are all to do with comparison. Okay, because you are comparing the mass of one atom, so you have to compare to the mass of one atom as well. But it's not very simple. It's 1/12 times the mass of one atom of carbon-12 isotope. Carbon-12 isotope is written as such. The 12 is on the top there to signify the nucleon number, because this is a carbon with 6 proton and 6 neutrons specifically. Okay, you might have seen it as carbon-12, okay, isotope. I personally like to write this. It's so much shorter than writing carbon-12. Yeah, carbon-12 means carbon-12 isotope, because carbon can have different isotope. Okay, so the 1/12 is important there. I don't want to go into detail as to why it's 1/12, but I hope you will have done this in class. What I'm trying to do here really is to outline the importance of the definition when you compare one atom to one atom, but you're comparing the mass of one atom, so you have to have mass of one atom. Okay, some books will have this term called an atom. Okay, so it's just the use of the English terminology really. One atom is the same as an atom, okay, because of the vowels and consonant. That's why you use an instead of a. I'm not an English teacher, so I'll leave it there. But important thing is people always confuse which one is average and which one is exact. Well, when you compare all of these, okay, ratio of average mass of, you will say one atom, but you don't say isotope, or you will say one molecule, or one formula unit of an ionic compound. Okay, so they're just different name really. I wouldn't say all. It's better if I don't say all. So atomic, you are talking about one atom. Molecular, you are talking about one molecule. The relative formula mass, you're talking about one formula unit of an ionic compound. Okay, so again, it's the same thing now, relative or compared to that. Guess what? These are the exact same comparison or relative ratio that you compare each of these two, except that these are all average masses, whereas this is just the mass of an atom or isotope. It's an exact mass. It's not an average mass. Okay. First difference, exact mass, average mass. Second difference, isotope versus an atom, one molecule or one atom, one formula unit of an ionic compound. But this comparison is the same. It's compared to the carbon-12 isotope. Okay, that's how you know that carbon 12 is a whole number, and you know that 12 there refers to isotopic mass. Okay, and you compare all of this relative to this particular isotope, carbon 12, which is the universally accepted standard ever since the, if I'm not mistaken, 1950s by the International Union of Physics and Applied Chemistry, if I'm not mistaken, IUPAC. Yeah, so it's an international norm now. Okay, so these are basic definitions that are very easily worth 1 or 2 marks. Okay, they are usually prior to them asking you a calculation question, and that is the basis of my video today actually. Okay, not to go through the definitions, but to go through the calculations to help you to see what are the different type of calculations that exist. Yeah, so they can give you, in this first example, these are isotopic masses. Look at them, they are whole number, all right, because we don't talk about decimal place when we talk about isotope mass. All right, so each of them has a percentage abundance. These are the thing they call percentage abundance or relative percentage. Sorry, percentage abundance or percentage by mass, I guess. All right, so to find the relative atomic mass, we multiply the isotope mass by the percentage by mass. So make sure you can use your bracket very carefully, because the most common mistake you can do is keying in things into your calculator which are incorrect use of bracket, and that will lead to serious disaster. So what you put at the bottom is the sum of the percentage. Usually they will come up to 100%, but I will never assume so. I will always calculate it just in case. All right, so why do I divide by the percentage? Why not divide by the mass? Okay, I'll tell you why. Your answer is a relative atomic mass. You are trying to get an average of these isotopic masses, right? When you take average of 24, 25, and 26, you are going to end up somewhere in between. So your lowest is 24, your highest is 26, your average is going to be somewhere in between. If you divide by 24 plus 25 plus 26, you will get an average between the percentage instead. Okay, that's why to get the relative atomic mass, we have to divide by the percentage itself, so that we will get a value which will roughly tell us the average, and the value will be somewhere in between 24 and 26, and that's how you can roughly tell whether you got the right calculation or not. Yeah, okay, because this is a calculation, what I will do is I'll do the top bit with the use of bracket very carefully, because you never know, calculators are a weird thing. And I'll write down the value specifically on top instead of just providing the final answer, so that when I have time to check my working, well, when I say I mean you, when you have time to check your working, you will find it much easier to backtrack your work and sum it up, and you can make sure the thing is correct, and then you can do the next part of the calculations, and you should be able to check it much faster. All right, they specifically want it to 4 significant figure, so not equal but roughly 3 3 4 6 3. First off, this value is somewhere in between 24 and 26, so that is a good news. All right, why is it very close to 24? Well, think about percentage abundance. You have quite a lot of the 24, not a lot of the 25 and 26. So that makes sense. When you have a lot of the 24, in fact more than 3/4, more than 75%, your average is going to end up much closer to you. I hope that makes sense to you as what it means by relative atomic mass. All right, going to example 2. The reason why I choose this particular example is because here, instead of percentage, these are what they call relative abundance. So what is relative? Relative, again, going back to the original definition, we talk about is the relative ratio of mass. Relative means it's a ratio. Okay, because it's a ratio, there are no percentage and there are no unit, because it's the ratio. All right, and the ratio here you can see is 7:3, and they add up to 10. They do not add up to 100. It does not matter because they behave in similar way. I could similarly tell you is 70% is to 30% of 63 copper and 65 copper. Sorry, we don't call it 63 copper, we call it copper 63. We call this copper 65. Just like you call carbon 12 isotope, right? But you write 12 carbon, just like that, okay? I know your periodic table, I think the modern periodic table, they might have shown the nuclear number at the bottom, but whenever you show isotope, please, okay? Whenever you show isotope, always show the isotope mass on top, okay? There's a standard that I've grown up with, and how I was taught in school. And suddenly when I look at the periodic table these days, they are just, I have no comment on it, okay? I'm not the one making the new periodic table. Anyway, so the relative atomic mass, it follows the same strategy really. So instead of having to convert into percentage, work in whatever they give you, because you could work in that. 7 is the relative abundance multiplied by the isotopic mass, okay? 3 is the relative abundance multiplied by the isotopic mass. Now, instead of dividing by the total of the percentage, because I still want the mass, right? I still want the average mass. So I do not divide by the sum of the average mass. I divide by the sum of the relative abundance. Whatever that I multiply for my relative abundance, I sum them up. Okay? It's not always divide by 100. Yeah, that's what my point is by showing you this example. That is to do with whatever information you are given. All right. So here I get 63.6. I do not need to convert to any significant figures, so I leave it there. Does it make sense? First of all, you have two isotopes, 63 and 65. You have a lot more of 63 than 65. Your average mass is in between 63 and 65. That is good to know, okay? Because you're doing average of 63 and 65, your average will be in between. It's closer to 63 because I have a lot more of the 63 than 65. So that is fine, all right? But of course, double check your calculation just to make sure that you've done it correctly. All right, we're progressing in difficulty across examples, yeah? So bromine exists as two isotopes, which is bromine 79 and bromine 81. So even though they give you the relative isotopic masses as decimal place there, we will use 79, 81 because there's specifically 1, 79 and 81, all right? So, how would I say this? You can tell that this is really close to 81 and this is really close to 79. Yeah, okay. I use 79 and 81, and this is the relative atomic mass. They want the abundance of these two isotopes. If you only have two isotopes, if this is 70%, then this is 30%. If this is 30%, this is 70%, because there are only two things in there, all right? Same with bromine. Okay, so you need to let something be something. Let the percentage abundance of 79 bromine be X. Could I have used 81 bromine? Of course, but your algebra needs to specify. Need to be specified exactly so that you yourself are not confused, all right? Because I'm talking about percentage abundance. Therefore, the percentage abundance of 81 bromine is going to be the total percentage minus that. Remember, we want both the isotopic abundance, okay? We want both of them. All right, so if I work in algebra format, then my relative atomic mass is going to be, well, I have X percent of 79 bromine, so 79 times X, okay, plus 81 bromine 81, sorry, 100 minus X percent, and then my total percentage was X plus 100 minus X, which I know was 100 because I have two isotopes. I work this out by subtracting from 100% anyway, and that is equal to the AR, the relative atomic mass, which is 79.90. Okay, so the bottom bit actually give me 100%, so I can move the 100 up there. It will give me 7990. 79x plus 8100 minus 81x. I will get 2x equal to 8100 minus 7990. So 110 over 2. That is 55%. Okay, but be careful, you haven't done this yet, and that is what they want. Okay, percentage of 79 bromine is equal to X is equal to 55%. Percentage of 81 bromine equal to 100 minus X equal to 45%. There you go. All right. And then, you see how the relative atomic mass is 79.9. It's quite close to 79. It's closer to 79 than 81 because even though it's almost 1-to-1, but you just have slightly more. You have slightly more of the 79 by 5%. That's why this value is just an average in between 79 and 81. It doesn't come to exactly 80. It's somewhere closer, slightly closer to the 79. Okay, so this is the kind of algebraic expression, algebraic manipulation that they expect from modern type of A-level questions. Instead of asking you to work out the AR, they want you to work out the percentage abundance. But the same strategy, the same format works as well, yeah? Alright, so moving on to a slightly more complicated example is that strontium has 4 isotopes. Just now we talked about 2 isotopes, right? So the difference between them are very simple, x and 100 minus x. But here you have a mass number of the 4th isotope, which you want to find. So let that be x, okay? So let this be x. So what is x? X is the mass number of the 4th isotope. Mass number of the 4th isotope. Then what is the percentage then? Well, you have 4 isotopes. I give you the percentage of 3 isotopes. Therefore, the percentage of the 4th isotope is equal to 100% minus, the use of bracket is again cannot be emphasized, yeah, cannot be overemphasized. All right, a lot of people struggle and they get the wrong thing because they did not use bracket correctly, only to regret it later on. Okay, so it's better to have the correct skill set from the very beginning. Yeah. So I know the relative atomic mass, don't I? They give me 87.71. So I'm going to find out the other one. So this is just the same as previous question, except that it's more tedious because it just involves writing a lot more and having a little bit longer calculation. So X is the mass number of the 4th isotope, is 0.56%. And because I was working in percentage, I could add this plus this plus this plus this. And I know they will add up to 100 because that was what I did in the previous question when I take away from 100. Okay, I hope you know what I'm saying, yeah? Well, if you don't, you can always add up the percentage. This plus this plus this plus this, you get 100. But it's the same as what I just did to get the 4th percentage. Okay, so 86 times 9.86 plus 87 times 7.00 plus 88 times 82.58. I get 8724 minus 0.56x. So what is x then? So x, I will move the minus 0.56x to the other side because they will make that positive. And then 8724 minus 8771. I've combined 2 steps into 1 step. Some people don't like that, but you can choose to write it if you want to. Whereas some people will find that, oh, you know, so trivial. Oops, I've done a mistake there. Because I moved this over to the other side, so have I done something wrong here? Why did that not match up? Yeah, I must have done something wrong here. Let me have a look. At 724. Oh, I know what I've done wrong. This should be a plus, yeah? Okay, no wonder it didn't make sense. So you see, it's very easy to make mistakes here and there, yeah? So you move that to the other side because that's positive already. So S771 minus S724 divided by 0.56. And I got 83.929. And if you leave your answer as such, you will be in big trouble. We talk about relative isotopic mass. Okay, it's the mass of one atom of an isotope relative to the mass of an atom of carbon-12 isotope, right? Well, times 1/12, of course, okay? Compared to the mass, 1/12 of the mass of an atom of carbon-12 isotope, blah, 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 okay? You have to run this up to the nearest whole number. Okay, because it's an exact mass that we are talking about. Okay, so it has to be 84 there as the mass number, and you cannot give this down as the relative isotopic mass because they don't exist as decimal by right. All right. The next example is a more complicated example because here, previously we have just been talking about atoms, elements, yeah, elements. Okay, so the individual atoms of the elements. Here we're talking about molecule. Okay, so I hope you know 35 chlorine and 37 chlorine. The relative atomic mass in the periodic table give you 35.5. that is average. Okay, that's because it's an average of these two, and you can work out, because there are only two isotopes of chlorine, just like the bromine. I hope you can work out the percentage of each. Yeah, and that's what they want you to do from this graph. Yeah, relative height of the peak, proportion of the two isotopes of chlorine. Chlorine 35, chlorine 37. Oops, not that. Chlorine 37 is that. Okay, so the chlorine have two isotopes, and what is the percentage there? That is a bit tricky. Oh no, it's not. So that is 10, that is 30. So to determine the proportion of the two isotopes, so 35 chlorine is to 37 chlorine. The relative abundance is roughly 10 is to 30, 1 is to 3. Okay, well, explain simply how you obtain the answer. You just look at the relative abundance, really. But they didn't tell you to, but I'm just going to work out the relative atomic mass of the chlorine now that I have the ratio. These are ratio, these are not percentage. But when you convert to percentage, this will be 25%, this will be 75%. But you do not need to convert to percentage, because you can work with you can work with this relative abundance, because you just divide by the sum of the relative abundance, and then you will get 35.5, which is what you see from the periodic table. Okay, but the idea really is the mass spectrum of the HCl. All right, so that's the important key thing there. Actually, I have to cover this. Okay, can you see that this is 35? So the mass over E, this is mass over charge. All right, so in the mass spec, everything is charged, because if your stuff doesn't have a charge of +1, you won't see it. Okay, the mass spec is not a stable species in the mass spec, so these are all reactive species. Yeah, but if there is not charge, if it is 0, then what you will see is something, you will not see anything, because it's 0 charge, right? So it tells you the mass, right? So this is 36. This is 38. So what is this 36 and 38 then? We are talking about hydrogen chloride molecule. So this is HCl, but it's H35Cl. So you need to be very clear in the mass spectrum. It's a 1H35Cl plus, whereas this one is a 1H37Cl plus. 1 plus 37, whole number, right? Because this mass spec tells you the exact mass over the charge. Yeah? 1 plus 37. So there's a difference between the two HCl molecule, because this is the one with 35 chlorine isotope. This is the one with chlorine 37 isotope. That's why they give you different masses. And you could always use things like mass spectrometry. Okay, mass spectrometry is the technique. Mass spectrometer is the instrument. Okay, to study their difference. All right. So example 6, which is actually the last question in these tutorials, it's a similar kind of concept. It's also quite tricky, but now you have a molecule. Okay, but in the mass spec, the chlorine 35 and chlorine 37, as you've seen previously, if you just have the atom, they will exist as the 3:1 like that. Okay, it's 35 and 37. But now you have a molecule. So what are the combinations? What would you see? In addition to 35 chlorine plus, so your mass over E, you will see at 35. You will see 37 Cl plus at 37. There's no problem. These are atoms. Why? Because they dissociate. So they break apart. Okay, atoms dissociate. I need to have better handwriting, really. Okay, so they could break apart, but you could also have the molecule. When you have the molecule, you need to think. When I have a molecule, I have Cl and Cl, right? So you have to specify exactly what are the species. 35 chlorine and 35 chlorine. Okay, all of them are positively charged in the mass spec. That's why there's a plus charge there. Remember, we talk about mass over charge. If something is not charged, you won't see it in the mass spec. This will give you 70, because 35 plus 35. So we are playing with combination here. Okay, we are playing with combination. How can you combine the isotope? to give you the different possibilities that you will observe. Okay, the key mistake to it is people might just think about the atom, or people might just think about the molecule, but people forget about the atoms that you will see as well in the mass spec. Okay, so this will give you 72, this will give you 72, and this will give you 74. Some people get all of this correct, and then they're like 1, 2, 3, 4, 5, 6. Oh, I will see 6 peaks. But this will overlap because they have the same. They have the same mass over the charge. If you have the same mass, you will appear at the same place. That means you don't tell the difference at all, okay? Whether it's 35 chlorine or 37 chlorine. And in reality, 35 chlorine and 37 chlorine is the same as 37 chlorine and 35 chlorine. I hope you can see that they are related by rotational symmetry. You can just rotate them along the axis there, and they are exactly the same. So altogether you see 1, 2, 3, 4. Okay, so both of them overlap. You see 5. So you see 5 peaks. These are a very good structure question. Actually came up from a multiple choice question, but it's a very good structure question because especially in an A2 setting, you could have a halogenoalkane, okay, where you can have different number of halogens, and you need to think about the mass spec fragmentation pattern, and they will ask you how many peaks will you expect to see for that halogenoalkane, etc., etc. So the concept has gotten more complicated, but I guess across most examination bodies of A-level, they would definitely have asked you to calculate AR, or work out the mass number of the isotope, or work out the percentage abundance of the individual isotope. So I've tried to cover all of that in the various examples within this tutorial video. So this is the end of this short tutorial video on relative isotopic and relative atomic masses. I hope what I explained within helped to clarify most of the stuff you will have learned in school as well as study in textbook. So I'll see you in the next video. If you have enjoyed my explanations and my videos, please subscribe to the channel and share the words and spread the love among friends and colleagues. All right, so thank you for watching. See you in the next video.